the last thing I want to do here is prove that the x coordinate of the vertex is at negative b over 2a. That was what I had said, that we will assume it to be true, that if we can find this, or if that's the case, then we can find the vertex quite easily. And here I want to prove it. So first off, we're going to assume that every quadratic function, of course, this is a quadratic function, has an axis of symmetry through the vertex. And it's going to be, horizontally symmetric. You can flip it across that vertical line and you get the same thing. And so what I have here is drawn a generic quadratic function. We have some vertex point here. We're not giving labels on anything because I don't want you to think of this thing as specific values, just the label thing. So this point here is going to be xv, yv, xv standing for x coordinate of the vertex. And then what we're saying here is that if we're assuming that every quadratic has an axis of symmetry through the vertex, that means if I take some y value, let's say that this is going to be, just give it some y value here. This is some value. And if I find this first point here, then that means across, if I go directly across to the right, across the axis of symmetry to the function again, that these 2 points here have the same y value. So I can say at this point here is some x value, x value here, right? This is x1. And then this point here has some other x value. So this point would be x2, but it has the same y value, whatever that y value might be. So this was at 4, this would also be at y value of 4, and so on. Okay, now I'm going to define these x values as distances from the vertex x value. So this vertex here is at xv. And so I want to use what's called epsilon. So this distance here I'm going to define as epsilon. Because it's symmetric, that means that this distance here is also epsilon. And I can use this to define x1 equaling the x coordinate of the vertex. If I subtract that epsilon distance, epsilon is just the Greek letter, that distance here, I get x1. So I take this thing, I subtract epsilon from it, I get x1. Then if I take the x coordinate of the vertex and I add epsilon onto it, that's what gives me x2. So I start here, I add epsilon onto it, I get x2. And because it's symmetric, if I go the same distance to the left as to the right, and I go up to the function, that I get the same value because of that axis of symmetry. That's what it means. So what I can do is that this function, of course, is just f of x. What I can do is I can say that f of x1, which is the same thing as f of xv minus epsilon, equals y, because you plug in the x coordinate, right? You plug in this x coordinate and you get out your y coordinate, is the same thing as f of x2, which of course is the same thing as f of xv plus epsilon. This is a long way of saying that I have this statement here. I'm gonna use this portion. This equals this. If you can understand how I got to this point, then you will understand the rest of it, because the rest of it is just algebra. And the reason why I can move on from this is because now I can plug it into my function. So I was plugging in xv minus epsilon equals xv plus epsilon. And now I can plug it into here. I get a x value is now xv minus epsilon plus b xv minus epsilon plus c equals a xv plus epsilon xv plus epsilon plus c. First off, you can see, well, I can actually cancel out the c's from both sides. And then I'm going to expand xv minus epsilon. Xv minus epsilon, of course, is just xv minus epsilon, xv minus epsilon. Same thing is true for xv plus epsilon. I'm going to actually distribute this whole thing out. I multiplied b through here as well. I haven't distributed a through there next. That's going to be the next spot. Okay, now I can distribute the a to the three terms here. And you can also see here I can remove the bxv from both sides as well. All right, double checking my terms. I think they are all good. Okay, at this point I can remove some more. I have axv squared on both sides of the equation. A epsilon squared, and that's the best I can do. I'm going to add these portions over to the other side so I have like terms together. Now we have 0 equals 4a xv times epsilon plus 2b epsilon. At this point, what I can do is I can divide by 2. 0 divided by 2 is just 0. Makes it a little bit nicer to look at. And I can factor out an epsilon. Both of these terms have epsilon in it, so I can just divide out the epsilon. I get 2a xv plus b. Now, for this thing to equal 0, either epsilon has to equal 0, this has to equal 0, or this has to equal 0. It's the same way when you're solving a quadratic equation. You have, like, for instance, x minus 2, x plus 3 equals 0. This must equal 0, or this must equal 0. And so you'd say x equal to 2 or x equal to negative 3. Well, the same thing is true here. If epsilon equals 0, that means that over here in our graph, if epsilon equals 0, that means there is no distance away from the vertex that we're moving, which means that both of these points, right, equal the x-coordinate of the vertex. That just means that both of these points are just going closer and closer and closer until they're actually the vertex. That's all epsilon 0 equal to 0 means. And that's not what we want. We don't want the 2 points to be the same point. We want them to be different, because if they're the same point, then all this thing is pointless, actually. So epsilon equal to 0 is not what we're looking for. We're looking for, when is this thing equal to 0? And 2a xv plus b equals 0 happens when, well, let's solve for xv. And then we divide by 2a. When the x-coordinate of the vertex equals negative b over 2a. And that is exactly what we wanted to find, negative b over 2a, right? Going back up to here. So the x-coordinate of the vertex equals negative b over 2a. That's what we were trying to prove. So that's the proof for it. The vertex is always located at negative b over 2a for any quadratic function. Even though this is here in the quadrant 1, and this one is open up. I did not assume that A was positive, or that it is all happens in the quadrant 1 on the coordinate plane. So this is accurate for every quadratic you can come across.